Okay, couple housekeeping measures. Your final is on the 14th at what did I say, 6:30? It's something like that. It goes to like 9:50 and something. Oh no, that's right. It's 7:30. That's right. It's 7:30 to 9:50. It's right. It's later. There is nobody in this room before that, so I should be in this room by 6 o'clock. So you do not have to necessarily wait until that time unless you have a test before, which in that case, wait, take your test. But I'll be here at 6 o'clock, so you can take your test at that point. That's not going to be a problem. That's that one. Second part, I'm not teaching Stats 2 next semester. I'm sorry. I'm teaching Calc 1 and Calc 2 next semester. But I am teaching quantitative reasoning in the winter session. So if you happen to need that class, take that over the winter session. It's basically 15 days and you get your 3 credits. So if you want that class, I am teaching that class. Next thing, so if you got 90 or A's on all your tests, you're exempt from the final as long as you've done all the homework and stuff. And Hawk, at least 80% of the homework in Hawks. The test is next Thursday, which won't really give you time to figure out if you've passed and got it before the final exam. So next Thursday's test will be on Hawks. So it'll be online. So you do not have to come to class to take it. You'll have 75 minutes to complete it. You'll have 1 attempt. It will not tell you if you got the answers right or wrong until Friday morning. So, or, well, if you want to wake up and be there at midnight, it'll tell you your score because it won't release the actual score, which questions you got right or wrong until the test is done. Because this way, to be fair to everybody, I don't want somebody to do in the morning go, oh, I got all the answers to the test and share it with everybody else. So this way, basically everybody will get the scores on Friday morning, and then you'll know if you got your 90 or above to be able to be exempt from the final exam at that point. I will also email you on Friday and let you know if you're exempt from the final at that point too, just to, in case you don't go look. Of all Hawks topics, yes. Yes.
Released at the same time?
Yeah, they're all going to be, it's going to be released at midnight on Thursday. So you have Thursday to do it. Oh. The test will be open. You have all day Thursday to do the test. Yeah, so you have it's going to take you have 75 minutes once you start it. You can't pause it or anything else. So once you start it, you have to finish the test. You have 75 minutes, and then but you won't get your grade on it. It won't tell you what you got right or wrong or anything else until everybody takes their test at midnight when it closes. It'll open up the grades. So even if you take it at 8 o'clock in the morning, you won't know your score until basically Friday morning. Okay, make sense? Yes.
How long did it take this test?
I will send it to you. Don't worry. Just send me an email to remind me so I don't forget, because I will probably forget. All right. I think that's everything I needed to go over. Any questions on any of that? Next Thursday, because I still have to finish chapter 11, which is this week. And next Tuesday will be the review for the test, same as always. I have it set so that it will have the T score, the T table and the Z table built into it. So you won't need those. It'll actually pull them right up there. And I will have the link to the website with the calculators and stuff on my site with the review day. So it'll have the review questions and stuff like that. And then the links on that will be all on my site. So you'll have access to all that. All right. Tuesday's review day. This week, Tuesday, Thursday, I have to do chapter 11. Next Tuesday's a review. No, I'm not going to get through it all today. And then next Thursday's the test. So, all right. Any questions? Okay. So, chapter 11 is in essence putting everything we've done so far together. Okay. We're going to talk about some new terms and stuff like that, but in actuality, you're not really learning anything different. We're going to do a lot of the same things. We're going to be looking at the Z-score. We're going to figure out if it's close and things like that. It's the same concepts. It's just putting it all together in an actual scientific way so we can make an actual conclusion based on the information. The two major things that you need to know is what's known as the null hypothesis and the alternate hypothesis. The null hypothesis will always be equals. And it'll equal whatever your parameter is going to is. So it'll equal your mean, it'll equal your proportion, things like that. So typically those are the only two you're going to talk about. If you get to stats 2, they'll talk about you can use this for standard deviation, for variance, and there's a few other tests that you can do as well. So your null hypothesis is always going to be equal to whatever your parameter you're looking at is. Okay, so the first ones we're going to be talking about, at least today, is they're going to be focused on the mean. Your alternate hypothesis is basically what you're trying to say or what that you believe to be true. Okay, so there's 3 different possibilities for that. You can state that it is not equal to whatever the mean is or whatever the parameter is. You can say that it is greater than the mean or parameter, or you can say that it is less than the mean or the parameter. So your alternate hypothesis is basically what you're trying to show or you're trying to support. The numbers that you use for both will be the exact same number. The only thing that really changes is the symbol between them. Your null hypothesis will always be equals. Your alternate hypothesis will be not equal to, less than, or greater than. But it'll never be equal to. Okay? Does that part make sense? Kind of, yes, maybe. All right. Did I put that where I think I put it? I did not. Put that over here. All right. So let's look at, this is the problem we're going to do a ton of work on. Okay. So this same problem we're going to do basically all the steps to. And I'm going to explain steps as we go for this problem. So this problem is going to seem to take a long time. And then we'll do another one that will take a lot quicker once we put it all together. Okay. All right. So suppose the national average or the average national reading level for high school sophomores is 150 words per minute with a standard deviation of 15. A local high school board member wants to know if a sophomore student at Lincoln High School read at a level different from the national average for 10th graders. The level of test is to be set at 0.05. A random sample of 100 10th graders from Lincoln High School has been drawn, and the resulting average is 154 words per minute. So the question that we're going to start with, the only thing that I've talked about so far, is the null hypothesis and the alternate hypothesis. So what do you think your null hypothesis is going to be? That the mean equals 150. That's your null hypothesis. What's your alternate hypothesis? No. What did I say about the null hypothesis and the alternate hypothesis? The numbers are always the same. So it's still going to be 150. We're not trying to prove that it's 154. What are they trying to prove? That it's different than the national average. So is it going to be not equal to, less than, or greater than? Not equal to, because we're just stating that it's going to be different. We're not stating that they're reading above that. We're not stating that we're reading below it. We're just stating that they're not reading at it. Yes.
The first, no.
Yes. That's why it's the O. That the O stands for null, and then the A stands for alternate. Or it's actually a 0. I shouldn't say an O. Okay. So yeah, this is your null, and this is your alternate. Does that make sense? Where we got those from?
So if we were if it were greater, then it would be like the high school's reading of it.
Above the national
Above the
average,
national.
yes.
Okay.
Yeah, that's what they would say. Or if they said it was reading below the national average, then it would be less than. But since it's reading at a different level They're not saying above or below. They're just saying it's different. That means it's not equal to the national average. Okay. So in essence, remember what we're looking at is we're looking at the perimeter. What are we comparing everything else to? We're comparing it to the average. That's that. Everything after that point is going to be used to figure out if this is true or not. But that's the parameter we're comparing it to, is the mean, the average. Okay? All right. So, first step, determine a null and our alternate hypothesis. Okay. Next step, we need to know what significance level we're going to use. So if we look at this one, what significance level did they set it at? That's our significance level. So our significance level for this one, 0.05.
What is that?
It's the A, it's alpha, it's the lowercase a, it's Greek letter. It's significance level. That's what they're used for. So if you notice, see it says specify the significance level at that A. That's just the symbol for significance level. You can use whatever you want for it, really. All right. The next step is we have to check our assumptions. We have to make sure that this is something we can do. Okay. So the things you have to check. First thing is it quantitative data? So is the reading score or the reading level or the number of words per minute a quantitative data? Yes. Remember, what's the difference between qualitative and quantitative? What's the difference between those two?
Qualitative, it's like very good. It's good.
Yeah, you really can't do calculations on it, right? Quantitative data, you can do calculations on it. Words per minute, that's quantitative. I can do calculations on that. Was there a random sample used to obtain the data? So let's look. It says a random sample size of 100 10th graders. So they did some kind of random sampling to get those 100 10th graders. So yes, it was a random sample. Was the sample greater than 30 or is it normally distributed? Remember that key number is 30. So as long as it's over 30, I don't have to worry about that. In this case, I had a sample size of what? It was 100. So we had 100 10th graders. So over 30. The next thing we have to figure out is, do I know the standard deviation of the population or do I not know the standard deviation of the population? What's that going to tell me? What did we learn before Thanksgiving? What was the difference between if I knew the standard deviation or if I didn't? No, it's not necessarily proportion. I gave you two different things. I handed out two pieces of paper in the past couple weeks. Z table and T table. That's the difference. If I know the standard deviation, I use the Z table. If I don't, I use the T table. Okay? That's the difference between the two. All right. So we've met that criteria. We've done that. Okay. All right. So those are the first 3 steps out of 6. So far, so good. All right. Next step. So there's 2 different methods to do this. We're going to do the critical value method first, and then I'll do the p-value method. But there's 2 different methods to do it. They're both identical. They're not going to take any extra work. It's just the way it is. Sometimes it's easier to use critical value. Sometimes it makes more sense to use the p-value. Sometimes it's just a personal preference on which one you like. They're going to come out to be the exact same answer at the end, and I don't think one's any less work than the other one. All right. So the critical values, we have to find the critical value, and then we're going to compare it. The p-value, we're looking for the probability. So critical values are your z-scores, p-values are your probability. The numbers inside the p-table. So those are really the only 2 differences in that respect. Okay. I already did the assumptions. I don't need that. Huh? Yeah. Because we know our standard deviation. So we can do z-score for this.
Well, is it always going to be your z-score and your probability? Like that's what those are?
Oh, critical value and
Yeah.
no, critical value can be could also be t. You could also use the t-table. Yes. Yes. And you're not going to be told you have to use one. Like it's not going to say use the critical value to do this. It's going to be whatever you want to determine it. Yeah. All right. That formula look familiar? It's the same z-score we've been doing for the past month. All right. I know the standard deviation. That's the only change. Do I know the population standard deviation is z? If I don't, I would be able to find my sample standard deviation because I'd have that data. So I would use t. So that's the only difference. And honestly, the formula looks exactly the same, except that's an S instead of the standard deviation symbol. That's the only difference.
So you use your table if you don't know your population. standard
Correct.
deviation.
Yes.
Okay, because that's why we had to keep solving for the standard
Yes.
deviation.
Yeah.
Okay. Cool.
Yep.
Cool. I had a note for that, but like that makes sense.
Yeah.
Here.
All right. So let's find the z-score for this problem. Actually, let me go grab the problem back. All right. So let's find my critical value. So what is my sample mean? That's the 154. That's the mean of the sample that I took. That's the 154. What is my mean of the national average? That's 150. That's the population average. Divided by, what's the standard deviation? 15. And what is the sample size? 100. So now I can find my z-score. So 154 minus 150, 15 divided by square root of 100. Equals 2.67. Okay. So far, have we done anything crazy? No. All right. So now we need to figure out what we're looking at. So, yes.
This is like, that's the same thing as the critical values. too.
Yeah. Yep.
Okay, that's how I ended up figuring it out, was I was just looking at the numbers in the critical value table.
Mhm.
On top is like confidence 1 minus X, or no, 1 minus A.
Yeah.
Because that's what like Hawks was saying, because I was really confused. Okay, that makes sense. Thank you.
Yeah, everything like circles back and is the same basic thing. We're just adding one step at the end and going, oh, now I can say this because I now know it. That's basically all we're going to say. All right. So the next thing now that we have, so I'm only done the critical value. I'll deal with the p-value on the next problem. So you can see how to do both of them. So my critical value is 2.67. I want to know if I need to, if I can reject the null hypothesis or fail to reject the null hypothesis. Okay. Notice that nowhere have I said I accept the alternate hypothesis. Okay. There's a very, like, it's very hard to understand why. It's like we can reject it, but we can't say for certain something else is going to happen. We just know that this didn't happen. Okay. That's all we can say. Right. So here's what we're going to look at. What was my significance level for this problem? Okay. So if we looked at our table, that was 95%, right? So what they're saying is that my 0.5 is going to be split between the two ends because I'm saying it's not equal. Okay, so that means it's two tailed, which means I have to look at both sides, which means it's not both 0.5. The whole total is 0.5 or 0.05. Okay, that's why it's 2.5 on this side and 2.5 on this side. If you look at that table, if you look at even the C table, at the very bottom, it actually tells you the Z-scores for 95%. They use 1.96. That's your critical value. Negative 1.96 and 1.96. Okay. What was my critical value? Okay. So that would be over here somewhere, right? So it's in my reject region. Okay. Did you go, oh? Okay. Does that make sense? Does everybody understand why it's in the reject region? Because that's the important piece. Okay. So when we're looking at a significance level, basically, remember the confidence intervals we were doing? We were saying we're 95% confidence between this and this. So if I look at my national average as 150 with my standard deviation of 15, I would say that I'm 95% sure that you're between this number and this number. Okay? And that would end up being whatever number is here and whatever number is here. If you fell outside of that, then maybe the national average doesn't work for you. Maybe you're not average. If you're between that confidence interval, then you're probably average. That's because I believe you should be in there. So in this case, with the numbers that we got, we're outside of that confidence interval, which means the mean might not be correct, which in this case means that we're probably not reading on the national average. Okay? Notice I'm not saying it's higher or lower. I'm just saying we're not reading at the national average. Okay?
Okay, I think
Yes.
my question is like, where did the 95?
Yeah.
What was the significance level? Right. So now think about where the 95 came from. I wanted the light bulb. I didn't want to actually say it.
Okay, that makes sense.
Because I figured if I said it, it wasn't going to necessarily click as well.
Thank you.
So you're going to see it both directions, actually. You're going to see them tell you the significance level is the percent, the number like that, 0.05. And sometimes they'll tell you to do a 95% confidence level. So you will see that written both directions. Okay? They mean the exact same thing.
Thank you for giving me an example written this way, because all the problems we've had so far
Yeah.
have been written the other direction. That's why, I think that's why. most
Yes.
of It's like good in here. That's why I kept looking.
Yes.
Like, there's no 95 written here.
Right. But if you think about it, 5% wouldn't make any sense to use. Because that'd be really tiny, and we don't have a 5%. The numbers we're typically going to use is 80, 90, 95, 99, or 99.9.
I found like 1.96 on here, and I was like,
Yeah.
okay, I understand that number. I see the 95, but I don't know where the
Yeah,
95
that's why.
came from.
Okay, so you're going to see it both directions. Okay. Now, that 0.05, depending on where you're looking, can change. So we were looking, this was the, go this way. Yeah, this was the two-tail test, right? So we were looking at both sides. That's why we were using the 1.96. All right. If I was only looking at one side, the whole 5% would be over here. So I wouldn't use the 95, I'd actually use 90, which we'll do one of those in a minute.
So anything that's in these tails.
If it's in those tails, it's in the reject zone. And I'm going to reject it. Okay. So we have now done step 5. We've decided that it falls in the rejection region. So we are rejecting the null hypothesis. They had like 7 pages on that. Like this one problem is like 7 pages in the book to explain to you why you're rejecting. I just want to see how they actually state the final statement.
So fail would be like if it's even further past that.
Yeah, if it's outside of that, where I believe it should be.
Wait, it should be in the 95%.
Right, it should be inside that 95%. If you're average, you should be in that 95%. If you're outside of that, you're probably not average.
So you reject.
So I'm rejecting the fact that the mean is 150.
So how far outside of that have to know? For,
If it's anywhere outside of if it's at 1.97,
but then why did you reject it and not fail?
you're never failing. Oh, wait, hold on. Sorry. I take that back. Oh, this statement. Okay. So never mind. I misunderstood what you said. If it's in here, I'm not rejecting, I'm failing to reject the null hypothesis.
Oh.
If it's out here, I reject the null hypothesis. We're in essence testing the null hypothesis. We can't test something that's a range. We can test something that's equal. Okay? So if it fell inside that green area, I'm not going to reject the null hypothesis, so it's probably average. Yes, that's what the critical value tells you. That's the critical value method. What? Go ahead, ask. Okay.
Did you just fail to reject? State it a different way? Like, because I think that's what's confusing.
I know, and there's a reason for it. Okay, so this is how, okay, I'm going to read this the way the book states it because wording really truly matters in how you state your final statement. Okay? And I normally don't read what the book says. I'm literally going to read what the book says. There is significant evidence at the 0.5 level that 10th graders at Lincoln High do not read at the national average. Okay? That's what we've determined because we've rejected the null hypothesis. So that's why it says there's significant evidence at that level that they do not read at the national average. Notice I am not saying they're above average. I'm not saying they're below average. Okay? Because we don't know that. We didn't test for the overachievement. We tested for, are they not average? Okay? So I can only state that. And notice I said there's significant evidence. I didn't say they are. Because we're only looking at 95%. If I looked at 99%, it might be different. Or if I looked at 99.7%, it might be even different. Like, so we're only 95% confident that this is true. Does that make sense? So this is why when we get our, this is the big disconnect between statistics and normal life. When we hear things, especially in the news and everything else, and say, we hear things as, this is the statement, this is fact. Okay, so we'll take the COVID thing and everything else. There's like, the COVID vaccine removes COVID or kills COVID, will prevent you from catching COVID. That's what the news article stated. None of the studies said that. None of them. The study stated that there's significant evidence to state as a reduced transmission, reduced everything else in it. It never said that it doesn't. However, we like to deal in absolutes. It's easier. It's nicer. It's cleaner. And if they said, oh, there's a 95% significance, like as soon as they stated that, the public would have tuned out everything they said after that. Okay? And that's where looking at it in terms of statistics and understanding how that works is important. Hey,
She's trying to help me and she
I got it. Just stop laughing. It's like, that's distracting.
If we fell in that 95% of the area, you could say the statement.
No, we would say that there's not significant evidence to state that Lincoln is different than the national average.
I guess I'm trying to figure out a different way to be able to reject in my head. So I don't mess it up when I go to.
Right, because you want to say, oh, it's over here, it failed. No.
Isn't it in Hawks that you just maybe can answer?
I actually don't know.
I checked it out. It looks like,
You might, at the end, you might check failed or reject. That, yeah. Yeah, I'm not sure how they did it,
Was
so.
there an outline of how we can write our conclusion?
sorry, that's what you're asking.
That's the entire, why
Yeah.
could I not English that correctly to ask you that? That makes so much sense.
You needed me to point it
I
out.
was like, where does the 1.96 come from?
Oh, gotcha. Okay. Basically what if you're going to state this outside of Hawks in a normal situation, you want to state what level you've done it at. Okay. So that's why I said there's significant evidence at the 0.5 level or 0.05 level. So you want to state the level you've tested it at or the 95% confidence level. You can say it either direction. And then if you're rejecting it, it says do not read at the national average or does not, whatever the average is. If you're not rejecting, if you're failing to reject it, you'd say there is not significant evidence to state that the 10th graders at Lincoln High read at the national average.
Or did that fail to reject?
There is not significant evidence. Okay.
And are we gonna have to write our conclusion?
I don't know.
No, I was looking at the practice test and it's like, you just choose like a wording choice.
Oh,
Okay,
I mean,
perfect.
I didn't know what I was reading, but like I was skimming through the test.
Yeah.
I'm like, this is a really long sentence. I'm gonna ignore that. But there's no, you're not like writing a sentence.
And I'm going to be willing to bet the differences between the sentences are like the words not, do not, things like that. So the sentences will probably all be very similar except for a few words. And those are the words that are going to make the difference between them. they're not going to be drastically different sentences to go, oh, this one totally makes sense. It's going to be those few different options. Okay. All right. Now, let's look at doing this with the p-value. So your the only step that we would do different is once we've got our critical number, we need to figure out our p-score. Or yeah, p-score or p-value, whatever you want. I call it p-score. So on your p-table, what's 2.67 give you? Yes. Maybe. I don't know if I have any more Z's. Hold on a second. I might. I have T. T. Wrong test. I'm doing great today.
That's what we've been using.
All right. Yes. Yes. There you go. You're up. Okay. Now I'm going to throw all this back in my bag. Yeah. There's T. Okay.
Can we find the p-score for those that we want?
Yep. So it's 2.67 on the Z table. Was it? Yes, we're looking at the Z because we're still doing the Z. Okay. If we do 1 minus this, we get 0.0038. Is 0.0038 less than 0.05? So my p-value, if 0.0038 is less than 0.05. Is that true? Then we reject. No. So it's like, again, you're just looking at taking that number and comparing it to the p-score, the number they gave you. So that's in essence it. This is easier to do on because sometimes that makes more sense for people when they're looking at the percentages than the critical values, but it's not much different. So it's like it doesn't really make much difference depending on which direction you want to go. Okay. All right.
So it's like critical value, it's more like a visual.
Yeah. Yeah. And honestly, you'll see me go back and forth between which one I use. It does, like I said, it doesn't. The p-value just it makes more sense because like, okay, well that percent's way lower than what it should be. They're asking me for, so therefore it works. So, but it just depends on which one you like better. All right, let's do this problem. A microprocessor designer has developed a new fabrication process in which he believes will increase the usable life of a chip. Currently, the usable life of a chip is 16,000 hours with a standard deviation of 2,500 hours. Test the hypothesis that the process increases the usable life of a chip. At the 0.01 level, a random sample of 1,000 processes will be tested. Okay. What is the null hypothesis? Yes. So my null hypothesis, no, not just 16,000. There's a statement. So that the mean equals 16,000. Okay. What's the alternate hypothesis? What am I trying to show? So what do they want to do? Greater than 16,000. They want to say that the process increases the usable life. So it's greater than 16,000. Yes. Oh, sorry. Thought I saw it. All right. They didn't give you that in that initial problem. Interesting. Answer. All right. So we've got our null hypothesis and we've got our alternate hypothesis. All right. We're doing this at a 0.01 level.
This one, I know.
So the 99 that you'd look at on the chart is a two-tailed version. No. This is just one direction. Correct. Okay. So that's going to be one of the distinctions between it. If you look at your t-table, actually, give me one step before we get to that point. Let's do the next piece. What's the significance level? We'll do this in order because I'm jumping and I don't want to jump. It is 0.01. Good. All right. Is it quantitative data? Yes. Is there a random sample? Is there greater than 30 that we sampled? Yes. Is the standard deviation known? Yes. Good. So we can do this problem. Yes. If the standard deviation is not known, we have to do our t-test. That's the change. Okay. If the standard deviation is not known, we have to use our t-test instead of the z-test. But the process, everything else will be the same except for that one calculation. Okay. All right. So we're good to that stage. Now we need to find our critical value or our p-score. So they don't give me the mean. We're going to use 16,200 for my sample because nowhere in this problem did they actually tell you, and then they used the number afterwards. So I'm going to say that equals 16,200. I don't know why they left it out. All right, so our z is 16,200 minus 16,000.
Can you go back? Why did you say 6?
I literally had to give it to you because they didn't tell you in the problem.
I was looking for it.
Yeah, I know. I looked for it too, and I'm like, they're missing something. And then I went to the book, and then it goes, okay, here. Because I'm like, why did they use that number? It's not in the problem. The actual sample mean. They didn't tell you the sample, like the actual value they got with their study. What's the standard deviation? 2,500. Oh, divided by the 1,000. Third of 1,000. All right, so we put this all in. And we get 2.53. All right. So what is my p-value for this? For 2.53. What was it? 0.9943. Okay, subtract that from 1. So 0.0057. We're looking for the little piece at the end. So this is what we got. We're looking for greater than, right? Remember, we're looking for greater than. So that means we're looking for this side over here. That's what's left over on that side there is 0.0057. Okay. And what was my significance level that I was looking at? Is that less than 0.0.01? Yes. So we reject the null hypothesis. Since we reject the null hypothesis, we can say there's sufficient evidence at the 0.01 level to conclude that the new fabrication technique is superior and leads to longer chip life. Okay. This time we can say that it leads to longer or it's greater than because the problem that we were looking at was greater than. Does that make sense? Yes? Okay. All right. Okay, so now let's look at this one. Actually, I think I already got this one in there. Yeah. Every problem they've done is reject. Like, all right, a personal researcher has designed a questionnaire she believes will take the average time of 35 minutes to complete. Suppose she randomly samples 20 employees and finds that the mean time to take the test is 29 minutes with a standard deviation of 8 minutes. Determine if there's significant evidence to conclude that the completion of the time of the newly designed test differs from its intended duration. Okay. So, what is the null hypothesis? $35. Okay, this one's 35 because the sample is 29. So the original statement was 35. So the average should be 35. That's going to be probably the hardest part for you to start with, is figuring out what the null hypothesis is and what the alternate hypothesis is. Remember, you're always looking at the what should happen, not what did happen. So what should have happened was 35 minutes. That was the average that this test should have taken. It only took 29 minutes, but that was a sample, not what should have happened. So that's where we switch these. What's the alternate hypothesis for this one? Correct. Not equal to 35 because it's difference. Means it could be greater or less than. What's my significance level? Okay. Now let's ask our questions to make sure we can do this. Is it quantitative data? Yes. Is it a random sample? Yes. Is the amount of sample done greater than 30? No. It was 20. Can we assume that it's normally distributed? Read the problem. It tells you that. It says assume the sample comes from a normally distributed. So we're good. Okay. If it's less than 30, we have to figure out if it's normally distributed, which either means we have to assume that or we have to find it. And this, they didn't give me the information to find it. So we're going to assume, they're telling you to assume it's a normal distribution. Okay. Because if it's not a normal distribution, none of this stuff that we're doing works. We have to do something totally different. Okay. All right. So it's normally distributed. So I can do this. Do I know my standard deviation of the population? Is that the population or the sample? Look at it. So in this case, it comes after suppose she randomly samples, but also you can look at your symbol. The S is the sample one. Okay. So in this case, that's the sample standard deviation. So we don't have our population standard deviation, which means we have to use our what? The t-table. Okay. We don't notice in the t-table you don't have the p-scores, so you can only do your critical value. You can't do the p-test for this one. All right. So now we have to look at this. Remember that the formula for t is basically exactly the same as the one for z. Same concept. So you don't really have to do anything different, except we're looking at a different table. So what is the sample mean? 29. The mean of the population was supposed to be 35. The standard deviation for the sample was 8, and we're doing it by the square root of 20. And when you do this out, you get negative 3.35. So that's my critical value. Because I don't have my population standard deviation. That's, yes. Yep.
Does it really matter?
What? The only thing that matters is which table you look at to get your answer.
If it's the same equation.
The equation's the same. Where you look is different, and that's the key. So we have to look at our t-table, not our z-table for this information. Because we have a critical value, not the z-score, like the z-score. We have to look at the c-score. This is now t, not z. That's the formula stays the same, the calculation stays the same, yes. Where we look to get our answer changes. Yes. Okay. Remember on our t-table, we're looking at, so the nice thing about this t-table is it kind of gives me the information for one tail and two tail. Are we looking at one tail or two tail? 2. So go on two tails over to 0.05. And where are we going down? What's my degrees of freedom? 19. Remember, degrees of freedom is 1 less than your sample. So 19 at 0.0 or 0.05 is 2.093.
I'm confused. Why is it
Yes. Because it says completion differs. It didn't say it was less than or greater than. It said it was differs.
Okay.
That makes it two-tailed.
If I see differs, I mean, it's always two.
Yeah. So, and this, your your alternate hypothesis tells you too. Since I said not equal to, that's two-tailed. Okay. Less than or greater than, one-tailed. Because we're only looking at one side. No, you can do two-tail on Z-score. We did that one already. Two-tail means the two-tail doesn't tell you which side you look, which one you look at. The standard deviation tells you which table you have to look at. If I have my population standard deviation, that's Z-score. If I don't, it's T-score. Does that make sense? Yes or no? Yes? Okay. So what is my critical value? Is 2.093. Or negative 2.093 because I'm on the right side of the graph in this case. And the one that I had was negative 3.35. So am I rejecting or not or failing to reject? I'm rejecting.
Well, I did it, like, what is that number for? Because what I did was I just drew out the chart and I put, like, because I got the answer negative 3.35, so it was outside of the 95%.
Yeah,
So
you
I
did this.
rejected. What is that critical value number?
You did this.
Yeah.
That's the negative 2.2903 is the critical value. That's how you determine if it's outside of the 95%. Yeah. The three, you said that's over here, right? Negative 3 point, what was it? 3. 3.5?
But instead of the negative 2 point, all that, I did 1.96.
You can't because that's using Z. That's the difference. So remember that the T distribution, since we don't know the standard deviation, there's variation in it. Because if you did the sample and I did the sample, we could get two different standard deviations. Yes. On your T table. So look at two-tailed from 0.05 and go down to 19.
Oh.
Because that's my degrees of freedom. Yes. So
And where's the negative?
it was on the where we're looking at the. I'm totally gonna screw up my left and right. Looking at the right side. That's why it's negative. Because remember, the chart's symmetrical. So you have that, the T is always going to give you the positive value. But remember, it's symmetrical, so it's both. Okay. So my number is negative, so I look at the negative version of it. Because if I was looking at this and say I got -1, I'm looking at that number right there. I'm going to say, oh, well, I'm rejecting it. Well, no, because it's on the negative side. I'd be looking at that number, not the positive version of it. So, okay, does that make sense? That's honestly the only difference between the two. It's like if we know the standard deviation, Z. If we don't, we use T. Everything else stays the same. I'm gonna do one more. As soon as I can find one, as soon as the book loads, so I can copy a problem, because these I cannot make up. All right. I never remember Hurricane Andrew. It sounds like you guys were I don't remember what year it went through, but some of you guys might not have been alive. So Hurricane Andrew swept through South Florida, destroyed South Florida, like literally leveled, like Homestead and that area. Like, historically, the average claim size was $2,400 or $24,000 with a standard deviation of $2,400. Several insurance companies collaborated in a data collection experiment. They randomly selected 84 homes to settle their claims. In the sample of 84 homes, the average claim was $27,500. So, question one, what is my null hypothesis? Yes, so that the average is 24,000. What is my alternate hypothesis? Let's see. Yes. And it says it would be greater than the historical average. Okay. All right. They don't give you this in here. I'm going to give it to you. So the significance level they want to test is at 0.01. Now, the nice thing is, again, remember, the T-table gives you your Z-scores on the Z-scores for those as well on the very bottom. So you can use this one table to find that information. Okay? So you don't actually need to look at your Z-score or the Z-table since all the ones you really need are at the bottom. All right. So, are we using Z or T? Do we know? I'm going to assume the rest of the stuff's there. Do we know our standard deviation for the population, or do we not know the standard deviation for the population? We do know the standard deviation for the population, so I'm using Z. So Z equals, what's the mean of the sample? 27,500 minus the 24,000. What was the standard deviation? 2,400. And what's the sample size? 84. Okay. And what do we get for our Z-score? Yeah, 13.37. What's the critical value that I'm looking at to compare this to? Now, you can look at this right now and go, I'm rejecting it no matter what. But what's the critical value that I'm looking at? Is this a one-tailed or two-tailed? One. So look at the top of your T-table. Look for one tail at the one. Okay? And then go all the way to the bottom to get the Z number. At the top, where it says one-tailed, right? And go over to the 0.01. Okay? And then go all the way down until it gives you your Z-score, which is 2.326. No,
The Z,
I don't think so.
13.
Yes, it really is that big of a number. I looked at it too, and I'm like, did I screw something up? Nope. What'd you get?
No, that seems like a really big number.
Yeah. It means that their average claim size was wrong. we'll explain the significance of this in a second. All right, so my critical value is 2.326. My Z was 13.37. So therefore, I'm rejecting the null hypothesis and stating that the average claim size is not $2,400 or $24,000. Okay? Yes. Now, go ahead, ask your question because I know what you're going to ask. Go ahead.
Because you said you were like, you can just look at the bottom of the T table.
Yep.
'cause I have, but that number is so big.
Oh, no. I'm not looking at 13.37. Okay. So critical value is comparing your Z-score that you got to what the significance level is going to be. Okay. So when we did our very first problem, it was 95%, right? Or 0.05. Okay. Which we said was 1.96, right? And we compared that number to 1.96. Okay. 13.37 is the number I got. I'm comparing it to 2.326. Okay. So it wasn't the question I thought she was going to ask. Oh yeah, I can do this. I can actually this one. No, because I don't have. I can make. No.
Anyway, so that's where you just go to like the 0.1, and that's you just pull the 2.326 for the critical value,
Yes.
and then you were comparing that versus if the 13.37, let's say that was like 2.0, that would be
Yes. Then I would have not rejected.
accepted, but
Yes.
it wouldn't be.
Not rejected. Okay.
Oh,
All right. So here's the. Actually, this was greater than, right? Yeah. So let's use this one. So this number right here was 2.326. And the number I have was 13.37.
Yeah, so is that everything greater than?
Yeah. Yes. I would reject my null hypothesis. This is the reject region. This is the not reject or fail to reject. Okay.
I thought you want to get greater than that, so it's,
I did.
if you get greater than that, I thought that means you fail to reject.
No. See? This area is reject. So if I'm over in this, if you ignore this side, I'm over here. So I'm in the reject region. Yeah, that was one of those ones like you look at it, you're like, yeah, that's just not going to be true. It's just not going to happen.
that's why I said we could compare it.
Yeah.
Because 1.337
Yeah, it's just so here is the reason why this one is actually historically significant. So what happened was the vast majority, when you have a national disaster, most claims just get paid out. They go based on data, stuff like that. They just pay you out. What they found was when they actually sent adjusters out to the places to actually do an actual, like figure out how much money they should have sent out, it was significantly higher, which means the people who settled and just took the check from the insurance company right away got screwed big time. So that's why this is historically significant, because what they found out was when they actually went through and did it, it was significantly higher than it should have been. So, well, you don't think $3,000 is a lot. Actually, I think Andrew was in 1991. 1992, sorry. So, yeah, I was going to say, most of you probably weren't even born. It hit just south of Miami. All right. We're going to continue to do this on Thursday.
we complete any section.
You should be able to complete 11.1 and 11.2. And if I remember, 11.2 has like 3 of them. It's like the 11.2A, 11.2B, 11.2C. You can do all those.
Okay.
I'm going to do 11.3, 11.4, and 11.6 on Thursday.
There was just like so many parts I was looking at 11.
Yeah.
There's so much. to learn.
Yes.
So if it's greater than, if it's right-tailed, then everything left
Over.
of it would be failed to reject.
Yes.
Okay,
Yes. So color that in. That's green means good. And over here,
this would also.
that would be failed to reject.
Okay.
Yes.
Okay, that's
Okay.
all I needed.
Yeah. Well, I
Did you
tried
do a
to-
steroid inhaler?
Inhaler, I got it.
She got everything.
Steroid inhaler is something you expect your best friend.
Well,
Except they make you jittery.
I'm like, okay, because the-
Yeah.
They make
You
you
walk
jittery.
around every 10 seconds.
All right.
I have a question about your quantitative reasoning class.
Yes.
Because I was literally just talking about that. Is there